Okay, hello everyone. Welcome back after summer break to the AutoML seminar. So it's my great pleasure to announce today's speakers, John and Oscar. So most of you might have been attending the AutoML conference last week in Berlin. And one of the central topics at the conference was automated machine learning for large language models. And I'm pretty excited about today's talk because I think it perfectly fits into this theme. Even if it's not specifically AutoML, I think it paves the way for this new, very interesting research direction. So yeah, without any further ado, please welcome John and Oscar. And yeah, John, please take it from here.
Cool. Yeah, thank you so much, Aaron, for having us today. So we would like to talk about our work, No Train, No Gain, which is co-authored by Oscar, who is also here today, Piotr, Pascal, and Matt Kastner. And so the outline of this talk is I will try to motivate why we look into efficient pre-training of language models. I will then argue that quantifying speedups is perhaps not as easy as it seems. We will then quickly talk about the experimental setup we consider, the methods we consider and evaluate, some of our preliminary results. And then lastly, in the end, we have a finale where we showcase the downstream task performances across all methods, which we believe is most likely the results most people are interested in. And we will end this talk with some recommendations and conclusions we draw from this work. So as perhaps people working on language modeling know already, training language models has been shown to be very unsustainable in the way that if you want to reduce test loss, you usually have to scale up either the compute, the dataset size, or the parameters, having the other two factors being fixed. And this is what people have called the scaling loss. This is mostly being populated by this paper, Scaling Loss for Neural Language Models by Kaplan et al. And we start with this hypothesis or this scaling law finding and want to emphasize that we believe this is fairly unsustainable. If you want to reduce the error by only a few percentage points, relative percentage points, you easily have to spend an order of magnitude more compute. And so this has motivated lots of works that aim to make pre-training more efficient. On the one hand, we have optimizers, which since forever actually have been focused or designed around convergence speeds, convergence rates, and so on, even in the convex setting. We also have methods that try to select the data sets that language models are pre-trained on. And many of these ideas also date back to old ideas from statistics. And perhaps a bit more recently, given the advent of the transformer architecture, where it's fairly easy to control the layers across the architecture, given that they usually have the same output embedding sizes, there has been more work around the idea of making architectures more dynamic and trying to figure out either during training or inference which layers are actually needed to achieve a certain loss. There are also other directions and works which we don't talk today about, but might be worth being mentioned, like other pre-training objectives, lower level, hardware level optimizations, parallelism strategies, and so on. And so the story behind this work is really more an unpredictable one. So we started by having a few of our own ideas on how to make pre-training more efficient in the way that we want to reach some pre-training loss with, for example, a smaller time budget. And we were mostly focused actually on the dynamic architectures front, on the transformer architecture front. And after a while, we realized and got disappointed over and over. And we realized that most of these ideas really didn't improve over the baseline we had. We will talk about that baseline very soon. And at some point, we then decided to also run more other methods prevalent in the literature that may have not been compared in our setting, which we will also discuss in a slide or so. And at some point, we ran all these other methods or we incrementally ran more methods and observed that many of them didn't really improve over this baseline. And at some point, we thought it might be worthwhile to write this up and to share these findings to understand what either we are doing wrong or what might be wrong about either these papers or either these methods or the experimental protocols in these papers. So let us start with reviewing some potential pitfalls of quantifying speedups as measured in number of training steps. So maybe as a question to the audience here, what could go wrong if you quantify speedups in terms of number of steps saved? Anyone here in the audience having some clue, you can also write in the chat.
I mean, if you have a selection operation that select the data for you, that has a cost and you don't factor it in.
Yes, that's a good point. Steps have very different time costs. Yes. I think that's pretty much spot on. So one very obvious, finding is or like conclusion one can draw by just thinking about it a bit is that different methods can have different walk log times per step. Another maybe a bit less obvious finding is, and this is not our finding, this has been shown in literature, is that if the baseline you compare against is not tuned for a specific budget, then it's fairly easy to beat it. So for example, if you look at a training run of a ResNet on JFT 300 by Kolesnikov, which is basically the BIT paper, you can see that if you, for example, stretch the learning rate schedule, you usually get a better performance towards the end, but the time it takes to get there is much longer. So the time to result is stretched by a lot. And so if you, for example, argue that you only want to reach a suboptimal performance somewhat earlier during training and your method is better for that, but you don't compare against, for example, the shorter schedule as shown here on the left side, then this is a somewhat unfair comparison. And something similar can be said about weight decay. Okay, what could go wrong if you quantify speedups in terms of flops? Anyone having an idea in the audience? Okay, so yes, flops don't correspond to walk log. Yeah, I mean, this is actually kind of the answer. So on the next slide, I will show you that, or I will make the case that usually we do care about walk log times in the end. And I guess the reason why flops don't always correspond to walk log times is, I would argue, because of the hardware we often have. So for example, if you look into the unstructured pruning literature of neural networks, you often see theoretical flops that can be saved in theory, but given the memory layout of current accelerators, don't exactly translate to the same speedups, or sometimes even any speedups in practice. So we would say that measuring flops, gains, or speedups is okay if you're aware of these issues and you act in good faith and you make sure that you do an actual apples-to-apples comparison. So for example, you fix the model architecture, you don't consider any sorts of pruning or dynamic skipping of layers or something like that, then this might be okay to do. But yeah, as Prabhu has said, I would still say that usually we care about walk log time. And so what could go wrong when measuring walk log times? My last question to the audience, and then I will not bother you anymore today.
Depending on which kind of machines you use, this may have a pretty high variance. For example, virtual machines have kind of different execution times sometimes.
Yes, spot on. So exactly, again, like in a hardware agnostic world, there might be nothing wrong with it, but in practice, it's very hard. For example, if you have different VMs, as you just said. And even sometimes on the same hardware, we notice that you can have fluctuations. We will talk about this in one slide. So let's maybe go through 3 scenarios that happen in practice very often. So one might be you have a single node with multiple GPUs in that node, and you try to run everything in parallel. If you run that and you even keep the software and hardware fixed, you can still have different runtimes depending on how many runs you have, like GPU or job completion runtimes, where you give, for example, each GPU a different job. And in practice, or sorry, in principle, you would hope that the different GPUs don't interfere with each other because you don't do distributed training. You can still have issues due to the CPU or RAM or other resources being shared. And so, for example, there is this one work which discusses this in the context of data loading. So this might be a pretty obvious one. But then another obvious one is, of course, if you have different nodes, different hardware, and this is probably very common in universities or smaller scale industry labs. We looked, for example, in the context of writing a rebuttal for this paper through the best papers of NeurIPS last year. And we found 3 papers where they detail in their appendix that they did use different hardware across experiments to parallelize the number of experiments and I guess to have results quicker. And this is okay in their context because these works were not considering training speedups. But of course, this makes a walk-log time comparison of efficient training algorithms a bit more complicated. And then lastly, we also digged a bit into this and found papers that argue that even when you have a shared industrial compute cluster, you can have job interferences, again, due to research sharing. So for example, Alibaba has a paper on this, where they, on the left-hand side, show the occupation of the cluster at different times throughout the week. And then on the right-hand side, you can see some variance across individual runs in each batch of a particular task. Okay, so this might be all very obvious, but how do we resolve this? So we propose something very simple. We propose to measure the reference system time. So this just means you select one particular machine, for example, one computing node with a NVIDIA 3090. You fix everything, you run a few iterations, for example, forward and backward pass in the context of training for the specific model you want to train. And later on, you use that measure as the standardized metric across all experiments and across all methods. So in practice, this is literally trivial to implement. You just measure, for example, once, okay, for this particular model with a batch size of 1,536, it takes this amount of seconds, and then you track that throughout training. And if that budget is reached, you stop the training. Another quick overview of our experimental setup is that we, in this work, pre-train BERT-based-ish models. We use the cramming model from Geiping and Goldstein and T5 base models. Our baseline is just using AdamW with a time-aware learning rate schedule. So time-aware here means that given the particular schedule function, we decay it based on the elapsed time and the overall budget we predefine. So the goal should be that we achieve one full cycle within the provided budget. And except for the data selection experiments, which Oscar will talk about, we use the C4 corpus, which is, I think, a very fairly often used corpus in language model pre-training. We consider 6, 12, and 24-hour budgets on common consumer hardware. And we want to emphasize that we did tune the hyperparameters of all the methods we consider here. Okay, cool. So let's dive into the first class of methods we looked into, the ones that we were also at first working on ourselves a bit. So one idea is model stacking. And the motivation of this line of work is that it has been shown in multiple works that if you look at the attention distributions of bottom layers and compare them with the distributions of later layers in the network, you see that they're somewhat similar. So here you have different heads of different layers, and you can see the similar patterns happen over and over again. And so what these authors argue is that, well, why don't we just train a smaller model at the beginning and then replicate it through our training by literally copy pasting the weights and stacking the model. And then in the end, fine tuning basically the overall stacked model. So for example, if your target amount of layers is 16, you would first start with a 4-layer model, train it a bit, stack it to an 8-layer model, train it a bit, then stack it to the 16-layer model. And on one hand, this is basically arguing for increasingly growing the network size, while now this method here, or this line of methods actually, argues for somewhat the opposite. So these lines of works of layer dropping argue that we actually want to start with a big model and then dynamically shrink the model through our training. And the observation they base upon this is that not all layers contribute equally to the loss reduction, especially through our training. And so we can reduce the flops per training iteration by skipping more and more of them through our training. And this algorithm basically considers two axes. It considers the time axis and the depth of the network, and thereby, or based on that, determines the probability of skipping a transformer block. And you can tune these hyperparameters a little bit, but overall, the idea is that later layers are dropped more frequently, especially towards the end of training. So as an illustrative look into the results we gathered, here are some plots about the training losses. So in terms of training loss, and here we want to emphasize that every data point is only seen once because we're like in a sub-1 epoch pre-training regime. We can see that stacking indeed achieves the lowest loss. But we can also see that the gap actually becomes smaller as we grow to 24 hours. And lastly, we can see that layer dropping basically never works better than the baseline in terms of training loss. And I will now hand over to Oscar, who will continue with this presentation. But if there are any questions up until here so far, I'm happy to take them.
There is one in the chat actually from Gabriella. I don't know if you can see it.
Oh, sorry, I didn't see this. Doesn't the RST overfit on a specific machine? For example, there could be a large speed up on this machine, but a slightly smaller on other machines. Yeah, this is a fair point, I would say. I think that you would need to take into account the hardware architecture you choose for the RST. So, for example, I would argue that if you look at the results in our paper, the actual hardware we used for RST may not be that important for the points we try to make, because for us, it's more about consistency. And we do assume that the hardware we used is somewhat general enough for future work to generalize from these. But if there are, for example, more novel architectures like the H100, which seems to work particularly well for semi-structured sparsity in networks, then yeah, this is something you would need to take into account and maybe warn the readers of your paper about. Does that make sense?
Yeah, it does. I would still perhaps verify on multiple machines. For example, if there would be some dependence on number of cores or something, it would be nice to see, like verify that the results are consistent across, for example, 3 machines, which is not so much, I guess.
Yeah, absolutely. Yeah. I think you could also consider having like multiple RST base measurements for different types of hardware to like account for this thing and then this kind of problem, and then producing your results for all configurations. But I guess we're quite resource constrained, so unfortunately we didn't do that. But yeah. Cool. So I actually that's probably not work, will it? I actually won't be able to see the chat during my half, unfortunately, but feel free to interrupt.
It was the same for me, but I will interrupt you if I see any.
Thank you. Does this work?
Yes, that's all good. Thanks.
Yeah. So Yeah, I'm going to talk about online batch selection methods. So these methods generally follow this kind of structure. So normally when we're doing training, when we want to fill a batch with items from the data set, we select them uniformly at random. But if we're doing online batch selection, then we use some sort of hopefully smarter method to select the items that we put in the batch. And we hope that by doing a smarter selection, we might be able to result in the training converging sooner, and therefore we can train faster. And there are various motivations for how you would choose your heuristic to select what items to put in the batch. And so we're just going to discuss two of those now. And the first one is selective backprop. So this was introduced in 2019, actually, for image classifiers, or at least that's what they look at. But we thought we would try it out to see if it works for pre-training language models as well. And the basic idea is that examples with smaller training losses probably make a smaller contribution to the gradients of the parameters. So this means that we may as well skip performing the backward pass for examples with small losses, because if that backward pass is not going to make much change to the parameters because the gradient is small, then there's kind of no point. And by skipping some backward passes, we can iterate faster, which hopefully means we can converge sooner. And so the other way you can look at this perhaps is that examples with smaller training losses, the model is already doing quite well on them. So there is perhaps no point training on them again because we're already doing pretty well. So the model has in some sense already learned them. So this is what the algorithm looks like. And so it's got two halves. In the first, we're selecting the data and building the mini batch. And the way this works is it's probabilistic. So for each example, we randomly decide whether to put it in the mini batch or not. And the probability that we put it in the mini batch is basically larger if the loss value of that element is more extreme, as in larger. So it's that's how it's computed. And once we've built the mini batch, then we can do the forward and backward pass like usual using that mini batch. But you'll know that there's an overhead here because now we have to compute all of these losses for points that we're not actually going to bother backpropping on. So then that's the first method. Oh, sorry, is there something in the chat? I can't.
Yeah, Oscar, there's a question from Luca, actually.
Oh, yeah, okay. Well, yes.
Could you repeat this question? So maybe.
Oh, yeah, sorry.
For the recording.
So Luca's question is, but you'd likely become more sensitive to outliers, which I suppose is quite a problem in large model or language model training. Yes, that is exactly correct, which brings us on to the second method we looked at in this section, which is row loss. And so this was introduced last year, and it sort of has language model training in mind, and it's motivated by exactly this problem that Luca mentioned. So if we're skipping points that are already learned by skipping ones with high training loss, that's good, but it also tends to focus on noisy points, so points in the data set that are just generally really hard to learn or are ambiguous, and then outliers, which are ones that appear occasionally in the training set, but there's not much point focusing on them because they're unlikely to appear at test time. And so that's not very good. But the idea is in row loss that if we use a second model trained on a holdout set, we can use the loss of this model to avoid points that fall into these two categories. So we can still avoid points that we've already learned by focusing on sort of fresh points, useful points, but by augmenting the way we're choosing the points, we can avoid these other two ones. And so the details of this are quite involved and probably out of the scope of this presentation. But here is a kind of summary of it. So you can see we're choosing the points by maximizing this row loss function. And this row loss function has two terms. And so the first one is just the training loss of the model. So if we just have this left one, then we're doing selective backprop. But then they add on to it a loss of the of a second model trained on this holdout set. And this basically counteracts for noisy points and outlier points. And it's quite interesting actually how this works, but we just if we go into it today, we'll be here all afternoon. So I won't. Yeah. So then the algorithm, again, I don't think we actually need to go into details of this, but just what I want to show is that, again, there's a lot of overhead here because we've now got, first of all, this ahead of time stage where we have to train a second model on a second data set. And then during training, we once again have this situation where we have to do a load of forward passes on some data points in order to decide what to put in our batch that we're actually going to use during the backward pass before we actually do the forward and backward pass. So this is just to emphasize there's a lot of overhead, and we will come back to that later in the results section. And so here again are a sample of our results, just to give you a flavor, before we look at the downstream results at the end of the presentation. So here we're looking at validation losses on the BERT model for a 12-hour budget. And the reason we look at validation losses here before we looked at training losses is because for these batch selection ones, the training loss is now influenced by the batch selection method. So it's no longer unbiased. So that's why we have to look at the validation loss instead. And here we're looking at 3 data sets, which are the 3 columns. And the reason we do that is because we thought, data selection methods might be heavily influenced by the data set. And so, yeah, so this is the validation loss over time. And you can basically see that, sadly, the baseline tends to outperform the 2 methods that are meant to be faster. And it depends a bit on the data set, but basically the baseline is performing well. And obviously, there is a lot of implementation overhead to adding these complicated methods. So that's not really, yeah, it's a bit of a sad news, really. Okay, so that's
just a quick question. Do you see? I mean, we also did some experiments, and we also had our share of disappointments from selective backprop. But do you see this kind of behavior only if you look at the work log time, or also when you look at, let's say, somehow the performance step by step? So is it something that is due to the overhead of the selection, or is something that doesn't make a difference anyway?
Yeah, so I think at the end of the presentation, we have a kind of what went wrong section, and I think your question will be at least partially answered then. Okay. If you can, yeah, I will. I'll come back to it then if that's okay.
Sure, I will stay until the end. No worries.
Yeah. Okay, so then the third case study we did was the final 2 methods out of the 6 was on efficient optimizers. And so the idea here is pretty simple. If we have somehow a optimizer that traverses the loss landscape better, then maybe we can converge in fewer steps. And if the overhead of each step is not much higher than the baseline optimizer, then we can converge faster in walk log time. And so going into this, we, to be honest, weren't that hopeful because new optimizers have been proposed quite a lot. And yet each time they've been proposed, things haven't really worked out. And so here are 4 papers discussing the various pitfalls of new optimizers that have been introduced. And so people tend to basically go back to the basics, to go back to Adam. But yeah, so when we were going in, this was kind of our feeling. This tweet here kind of summarizes it quite nicely. So, here we go. Another new optimizer. Is it going to work? And, this time it's different. But maybe this time it is different because these 2 optimizers are claiming speed up specifically for large scale models. And there's loads of hype on Twitter and there's lots of stars on GitHub. So surely they must work. So we were kind of hyped. And so the first one is this optimizer called Lion. And this is cool because I guess probably relevantly for AutoML, it was discovered using an automatic discovery process, basically. And so there's no underlying theoretical idea for why it works, but the automated process tried out loads of optimizers, and this one worked quite well. Oh, cool. Okay. Well, I guess you're all probably experts on this one. Oh, Aaron says this was actually a talk at the AutoML conference. Yeah, so that's Lion. And it's cool because it's simple to implement and there's not much overhead. And they report lots of speeds in their papers, so pretty exciting. And then the other one we looked at is one called Sophia. And so this is a second order optimizer, and it was designed in a more conventional fashion by hand by people thinking about what would be good. And they claim a huge 2 times speed up in their paper. So, wow, so, you know, it's going to be really good. And just to summarize it quickly, this is their gradient update function. So on the left here, we've got the new parameter, and then on the right, this is the old parameter, and then this is the update. And so what's going on in here? Well, this M thing is a moving average of the gradient of the parameters, and then it's being preconditioned by the Hessian. And so the idea is that this allows, I guess, the optimizer to adapt better to the curvature of the loss surface. And then there's a load of stuff basically to stabilize it. And then this is the learning rate. So that's an overview of how Sophia works. So then did it work in practice? Well, here are our training curves again. So we'll discuss downstream tasks at the end. And yeah, it's, well, as you could probably guess, it's a bit disappointing. So on BERT, Lion actually did perform a bit better, particularly as the training budgets got longer. So you can see here, oh yeah, so this left plot is the loss over time for BERT. And you can see that for the 12-hour and the 24-hour budgets, Lion is starting to perform a bit better than the baseline. The colors aren't very good here, but hopefully you can see. The bottom line is Sophia in these cases, is Lion in these cases. But sadly, Sophia performed worse. And then in this right-hand plot, we've got the T5 experiments, but here it was bad news for both Lion and Sophia in these experiments. So I don't know. It's kind of exciting that Lion seems to be doing a bit better, but maybe things aren't as, you know, as exciting as we'd hoped. So yeah, so up until this point, we've basically been looking at the results during pre-training, so the pre-training loss and sometimes the validation loss. But I guess what we've got to do is look at the actual downstream task performance. So the question is, like, on the downstream tasks, so we pre-train the base model using one of the speed up methods, and then we try it out on a downstream task. And so the question is, if we use a base model pre-trained with one of these speed up methods, does it do any better on a downstream task at the end? And by this point, you can maybe guess how this is going to go. So lots of tables. I guess if you're interested in the details, we would love you to look in the paper. But over on the left here, we've got the results on BERT. And then so glue and superglue are two downstream tasks that people tend to use for BERT type models, and then SNI is for T5. And so, yeah, obviously I won't go through all the results in detail, but we've got the summary of the points down here. So the first one, yeah, is that basically in most cases, for most budgets, the baseline either performs the same as or outperforms the speed up method. The exception is layer stacking, which we can see over here. On T5 on the shorter budgets, layer stacking is actually doing quite a bit better than the baseline. So that's exciting. And then, but then once you get to the larger budget, the baseline overtakes. And it's a similar study in similar situation in BERT, where layer stacking is doing quite well for the shorter budgets, but then by the time you get to the 24-hour budget, the baseline has started to catch up. But it's still kind of interesting. Maybe there are some situations where this would be useful. And then for the 24-hour budget, no method is beating the baseline. Some of them are drawing equal. So yeah, so I guess in the last bit of the talk, we wanted to discuss like a little bit of what's gone wrong. Yeah, okay. So David says, do you think some of the bad news could be because of the specific setup for the speed up made in the cramming repo? Also, maybe those things only work at large scale, which would certainly weaken the claims made. So yes, I think this is definitely true. So there are some specific things we notice, which I'll come on to next, but obviously our results only hold in the specific setting we consider. And so if people aren't familiar with the cramming repo, it's basically the idea is to do as well as we've got a pretty small budget. So you've got 24 hours on a single GPU, and you want to do as well as possible in that small budget. And this budget is much, much, much smaller than the one that was originally used in the BERT papers. So the idea is like we try out this small budget, you know, and see how well we can do, even though this is a much, much, much smaller budget than in the original paper. And so, yeah, the reason we selected this is because we think it's a really strong baseline. So one hypothesis is that these methods don't do as well when your baseline is really strong. The other hypothesis is that, yeah, they work better when the scale is much larger. And that could be the case. Maybe... yeah, I don't know. Jean, do you have any thoughts on like how many of these papers were training on realistic scales themselves? I mean, for example, the Rolos paper discusses large language model training, but then, you know, large language model training at the limits of, you know, tens of or hundreds or thousands of GPUs, but then only does experiments on single GPUs on small ResNets. So, you know, not all of the original papers were looking at large scale situations as well.
Yeah, maybe just one more comment on this. So the T5 experiments we ran, we used a repo for that was also by an academic researcher, by Piotr, who is also a co-author of this work. But if I remember correctly, so in the Cramming paper, there are definitely a few whistles and bells and a few things that have been tried to already improve the performance for this academic budget. I would think that, if I remember correctly, it was a bit less than that in the T5 repo we used. But of course, like as with many different repos available and implementations, and especially I think in language model pre-training, where there are very often much more whistles and bells than, for example, in image classification, which was often considered in some of these works, I think there can be discrepancies across different repos. So, of course, this is like a disclaimer we should emphasize here again about these results. But so far, we haven't, like, until we, since we have put the paper out, we haven't heard from anyone that they had different results than the ones we did. And I mean, it would be awesome to get like a different perspective on this. By people maybe having more compute and scaling these things up more.
Cool. Yeah, so then the last bit of the talk is just, yeah, to look at a few things that we noticed when we were looking at all of these papers, which also worth discussing. Yeah, in a sort of what goes wrong section. So the first thing we noticed in quite a lot of these papers, actually, is that people are effectively using the wrong learning rate schedule. So this is a figure that I have taken from the selective backprop paper, and it shows the test error of their models against wall clock time. And you can see in blue here is the baseline, and then this pink line is selective backprop. And in this experiment, they're using a stepped learning rate schedule because I think they're training on some sort of image model. And so you can see the steps here. So the test error has this big drop here and then another big drop here. And so both of these big drops are a drop in the learning rate. But you can basically see that the model only reaches its final performance when the learning rate reaches its lowest value. So the learning rate needs to be almost 0. And so what this means is that the time at which the model reaches its final performance is heavily influenced at the point at which the learning rates are dropped. And so this is also true in language model training, where people tend to use a sort of smooth learning rate decay schedule rather than these drops. But the same principle is, occurs, that the learning rate has to be decayed almost to 0 before the model reaches its highest performance. But what you'll notice is that between all of these different models, the drops are happening at different times in wall clock time. And so why is this? Well, it's because they're decaying the learning rate as a function of steps rather than of time. So because selective backprop, which is this pink line, is iterating faster, it's going to reach the step at which the learning rate should be dropped sooner than the baseline. And so what this means is that when we look at this in terms of wall clock time, selective backprop is kind of getting an unfair advantage because its learning rate schedule is sort of accelerated compared to the baseline. So you can imagine that if we change this plot so the learning rate schedule was done in terms of wall clock time rather than steps, then all of these drops would be happening at the same time. And you might imagine that the baseline might actually achieve performance close to or potentially equal to selective backprop at basically the same time in terms of wall clock time. So this, if you make this mistake of scheduling your learning rate scheduler in terms of steps rather than time, but then you make your plots in terms of time, you sort of get this, it appears that there's a speed up happening when actually there potentially isn't. And we saw this quite a lot. And in fact, it's, you know, an error we were making to start with as well. So it's not at all obvious. And so, yeah, so we make this recommendation that for a fair comparison in these speed up papers, you need to pick a fixed time and compute budget. And then you need to set and measure your performance within that budget. And then you need to set the learning rate schedule and any other schedules based on time rather than steps. Because, yeah, otherwise this kind of thing is going to happen. So that was one thing we saw, and in a surprising amount of papers, actually. And then the other reason that we think our results might differ from results, well, one reason why these methods are, you know, not resulting in speed up is basically that overheads are expensive, which is a very obvious thing to say. But if we consider the data selection methods, you have to, you know, you have to do really well at your data selection in order to outweigh the extra cost of doing the extra forward passes you have to do the data selection. And this problem is going to get worse as the model gets bigger as well. So yeah, it's actually quite tough because you're basically doing a load of compute and then sort of throwing it away. So you have to, yeah, it's quite a high bar to clear to overcome that. And then, yeah, for Sophia, the same kind of thing arises because they have to do this Hessian update, which requires doing a load of forward passes. So your optimization algorithm has to converge quite a bit faster than it would have done in order to overcome this overhead. So then to look into this a bit, we actually did some experiments where we ignore the overheads. So what we do is that basically we're recording the time that the model is trained for using our reference system time clock thing, and we can basically just ignore additional forward passes from this counting. So the model gets more time to train because we're ignoring the time that is taken by these forward passes. And so on the left here, we've got some downstream results that we had before, where we don't give the data selection for free. And then on the right-hand side, we have the same results, but where we gave the data selection for free. And you can see that the performance of the models gets quite a bit better from right to left. So this does make a difference. And selective backprop, you know, starts to potentially beat the baseline. So then I guess the question is, like, is it realistic to ignore these overheads? And to be fair to both these original papers, they do discuss, you know, that you could use some sort of distributed system to do the batch selection. So you could be training your model on one set of computers and then doing the batch selection on another. But as far as I'm aware, no one has actually ever shown that this works in practice, because that will have its own overheads. But that's quite an interesting idea, potentially. Does that answer the question from earlier?
Yes, thank you.
Perfect. Yeah, so just quickly, our conclusions from this work. Yeah, so our takeaway was that a lot of speed-up methods, maybe this is overstated, the ones we looked at aren't worth the extra implementation complexity because the benefit is definitely not, you know, guaranteed, and in fact is likely to potentially make things worse. So it's not worth the extra work implementing these things potentially. And then, yeah, we have this recommendation that, you know, rather than trying to measure speed ups in like a multiplicative way that as people tend to do. You should instead train to a fixed time compute budget and then set the learning rate schedule based on time, as I mentioned. And then we also think people should be more careful about how they're measuring the budgets, because a lot of people use flops, but yeah, are flops actually the correct measurement? And you could use RST to do this. That's what we've come up with. Maybe someone could come up with something better. If you want to use RST, you know, we've released our code and timings on GitHub, so feel free to use that. Yeah, and so the paper is on archive and the code is on GitHub. Yeah, and we're very grateful to these other two authors who wrote these fantastic repos that allowed us to implement our experiments very quickly. Yeah, so that's the end.